Okay, good evening, everyone. How are you guys doing? Happy or sad about the last lecture? Really? Okay. So I was just trying to compile these experimental videos that I'm trying to screen record. So they are available on. So somebody had asked for recordings some time ago. Is A Gupta 44 here? It's not here. But so this is a playlist of. I guess I think that's a playlist, right? It's just one video. I think yeah. So this is this semester's recordings, unofficial. If you need it for your exam preparation, okay. It has lectures till last lecture, so hopefully it will help you with your preparation. Okay, you can find the link. So I have to still clean them up in terms of trimming some initial and break parts and so on, but you will be able to find the lectures on that playlist. Okay, and so how was the submission for assignment 5? Were people able to do it? Was it too easy or? Okay. 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 So are assignment 4's grades out? Not yet. 3 is out, right? Okay. So we'll try to get as much as possible soon the grades. So this is the pretty much the last lecture before the exam, and today we're going to look at time series models. They are, if you did not know time series models, we could just use supervised learning, and we'll discuss that. Actually, it's a huge area with its own courses, right? Time series methods. So today we'll just touch very few, just extreme beginner ideas in time series modeling. Okay, so let me just flash the. So basically, you've already, so when I covered EM and, okay, EM is there. So when I covered EM and I talked about maximum likelihood estimation, there was this notion of joint distribution, and there's been a notion of joint distribution for several of our models that we have seen in this class. But you'll see that time series can also be viewed as a certain type of joint distributional assumption. Okay, and that point of view makes it not a mammoth to conquer. I mean, something which is easy to get to if you're strong on the foundations. So today we look at what's the difference between a time series data set and a regular supervised learning data set. It's a very simple idea, which is that there's dependence across observations. The second point is how to model such dependencies, and we'll see that, okay, you can always do have some huge joint distribution between, if things are related to each other, we can have a huge joint distribution between the things that we want to relate to. But maybe sometimes it's hard to maximize such a likelihood function or a joint distribution, maximize the parameters to get a high likelihood value. So then there are some ways to do it in a more, I guess, parsimonious way. By parsimonious, I just mean not thinking about the joint distribution, but directly thinking about things like correlations and expectations and so on. And that's kind of what we'll touch upon today. So point 2 is about how to model dependencies across time, not just as a joint distribution, but maybe with simpler objects like correlations and means. Okay, and we'll look at the third thing. Is going to be what are called autoregressive moving average models. So we'll actually not really spend any time on estimating the parameters of these models, because they are actually, it's a full lecture by itself. But we'll look at what is an ARMA model, what are their parameters, and what do they capture. Okay, some ideas about it. And last point, but it's it's not a separate topic, but we'll just keep discussing, okay, we've already learned supervised learning, how can I reuse them for time series models? Okay, so that's the agenda. Any questions? So how many of you have already done a course on time series? Not a course on time series. Okay, it's a very important part of a lot of data collected on, especially online data, marketing data, sales data. There's going to be temporal patterns, right? So so it's important to kind of at least appreciate, what you should know, hopefully, maybe when you take a full lecture, or just pick up some books for reading about time series methods. Okay. So with that, let's actually, and then so actually we will not cover too much about time series, so we'll spend some time on review of topics for the exam. Okay. Okay, so we again switching gears. Unsupervised learning, we already saw some somewhat complex methods, k-means, k-medoids, and PCA, as well as spectral clustering. So today we'll kind of switch gears back to supervised learning. So where actually we don't even need supervision. So we may even, so when we talk about time series, we don't even need to have supervision. You can just think of some relation between just labels themselves, or just a quantitative variable, the y's themselves. Okay, you don't need x's as well. X, the features, you don't need the features. You could directly model the y's. Okay, and that's, so think of a sales column in your tabular data set. Then you can just model something on just the sales observations, right? So we'll see that. So it's even, I would say, subset of supervised learning. I mean, needs less data than supervised learning because it's a slightly different application. Okay, so for us in supervised learning so far, there is this xi, yi, which whenever we wrote from here, right? So given this, we wrote this loss function, sum over 1 by n, I is equal to 1 to n of L of f of xi, comma yi, right? So this was a proxy for the expectation, okay, with respect to the joint distribution between x and y of loss of x, sorry. Okay. Right, just we don't know the expectation because we don't know the true distribution, but data was from the hopefully the true distribution. So this actually assumes something, which is the independence across observations. Okay, so observations across the observation indices here are independent. Okay, and in fact we assume that each observation pair, xi, yi, are sampled from this P of x comma y, right? And so we have already used not just little x, y, so we actually used capital Xi, yi when we talked about generalization error and so on. So we assume that these are sampled from the same distribution and independent of the next observation, for example, xj, yj, or xi plus 1, yi plus 1. Okay, so that was the key assumption. That's not needed for actually just running through an algorithm and getting some output, but it's needed to kind of justify why you would choose an average of loss functions for losses for each observation, and why is that a good proxy for your test error, why is it a good proxy for your training error, and so on. Okay, so independence was assumed, whereas what in time series what we actually want to capture is the relation between xi, yi, and let's say xj, yj. Okay, so these are, let's say, 2 rows of my data. Then I would be interested in relating this. Okay, so that's the series aspect of the time series aspect here. And there's different ways to measure relationships. For example, you can directly jump to things like probability, joint probability. So xi taking a value little xi, yi taking a value little yi, and xj taking a value little xj, and yj taking a value little yj. Okay, so this kind of captures how all these random variables covary, or not just covary, but how they simultaneously take different values together, right? So there could be dependence on how xi and xj simultaneously are high or low, or whatever the values they take, right? So this is one example. The second example is through simple things like correlation. So correlation between xi and xj, or all the other pairs like xi and xi and yi hopefully are correlated. Otherwise, you will not be able to make a prediction. Otherwise, if they're not related, correlation is just one way to say that random variables are related. So you could have correlation between xi and xj as a way to say they are related. Okay, they may simultaneously take both high values, or one taking high value implies the second one may be taking low values. Okay, so that's one way to capture this dependency or relation between multiple observations. And in a data set, right, x1, y1, x2, y2, all the way to xn, yn, the order relationship becomes important. So the order is important. Okay. So I can't arbitrarily switch two rows of for example, my data. Okay. So you could think of xi, yi separately, or you can just write z1, z2 to zn. So there's an order relationship between. Sorry, this is just an arrow, just showing to say there's an order relationship between these observations. Okay, and you can see here this loss function here that which I'm highlighting towards the top right. There is no order relationship. Okay, it's a symmetric function in the sense that I can flip two rows and it's the same loss evaluation. So if I flip my data, randomly permute my data, evaluate the loss for a given prediction model, it's going to evaluate the same number, maybe 0.4 or whatever, right? So that way it is kind of ignorant or invariant to order relationship, that loss function. But I mean, in time series, we do care about the order, okay? So what are some applications? I mean, many of you already know several applications. I just mentioned sales data. So here in the notes, I'm talking about like financial analysis, like the dynamics of viral media, so advertising or clicks, or like there's a movie that got released, right? So how is it doing in the box office? There's a temporal relationship, which is kind of critical for analyzing, that for that movie or in general such data sets. Okay. So in time series, as I was saying earlier, you don't really have to explicitly think of. So the simplest version of time series models work only with just yi's. Okay, so which means that I don't have to think about features to think of a full-formed time series problem. For supervised learning, I need to have something predicting something else, right? X's predict y's. Whereas for time series, because I care about, my first order question is about how do I model the relationship across time or across observations. I can just focus on let's say even one variable or one feature coordinate or just the outputs. Okay, so that's why I'm saying that we can just think of z1 to zn to be the bunch of random variables 1 to n, and they have this order relationship between them. Okay. And actually, yeah. So there's so just to ground, I think this is kind of obvious, but let's see. So this was an example of a time series data from, I think, the first lecture, which is from some project I did several years ago. This is the lap times of NASCAR, lap times in seconds of okay, of the all lap times across 500 laps. Yeah, all players lap times across the 500 laps in this particular race. So this race had 500 laps, and I'm just plotting the lap time. So you can see that there is some temporal aspect to this, right? Things are increasing. So if I arbitrarily permute the lap indices, then it'll look like noise. Okay, as in you will not probably eyeball the pattern that we are eyeballing here. Okay, so it's just an example of a time series data set, and you've seen stock market data and all that, which has similar observations. Okay, so let's start with let's start with a simple observation that to capture relationships, the gold standard is just a joint distribution between random variables. So if I have n random variables, I can just write p theta of z1 all the way to zn, right? So this would be some joint distribution. I haven't told you what the joint distribution is, but if there was a parametric distribution like this with some parameter theta, then this captures a relationship between all these random variables, and it could be that these just to contrast in like if there's random variables for IID, there is no order relationship, then you would just write probability of z1 to zn to be just the product of, let's say they're independent, okay, product of ci, I is equal to 1 to n. So here there is no ordering information, whereas here, because I explicitly wrote it as a joint distribution, you could capture order relationship. Okay, for example, you could say this is the product of I is equal to 1 to n minus 1. Actually, I is equal to 2 to n minus 1 of probability of zi given zi minus 1 times probability of z1. Okay, so this is an example of joint distribution. Yeah.
In this case, your z is both the x and the y.
Yeah. So I was just saying that 2 minutes ago that we don't have to think of x and y, because we in time series analysis we care about temporal relationships. So let's think of the simplest problem. So let's say we only have y's. We don't even have features.
So in this case, your z is your y.
Yeah, it could
not
be. Yeah.
The x and the y.
Yeah. Yeah, you can make it x and y as well, but it doesn't. It's not important for this point. It could be x and y. It could be just y. It could be just one of the features. Okay, just think of y as sales data, or z is a sales data. So think of sales being the output variable, and I don't even care about features now of anything. Then this is so. I think 2 slides ago I just said that this is the best. I would say I'm saying it's the best way to capture relationship between random variables. And here I was just illustrating that if the random variables are independent across observations, there's no order relationship to be maintained. Maybe, for example, that could be one example of a situation where there's no order relationship. Each random variable is separately drawn from some marginal distribution. Then you don't care about what order it comes from. And this thing in the box was an example of a joint distribution where I have written there is some ordering that you need to care about, because for example, zi taking some value depends on what zi minus 1 took. Okay, so this is, I guess, the simplest I guess this first level logic that you should understand. Can you guys see why this captures some order relationship? Any questions about this part? Yes.
What is I equal to in that one?
I is equal to 2 to n. Why is it 2? Oh, it doesn't look like 2. Because I wanted to start some summation. I had to cover all the n random variables. So I started from 2 to n. So 1 is remaining. So I just added that guy here. And I said given z1, z2 will take. So the value z2 takes depends on what the value z1 takes. Okay. So this is an example of something which is capturing order relationship. If you remember just the definition of a joint distribution, then this probability is equal to probability of z1 this is just what is called just a factorization. Okay, probability of Z2 given Z1 times probability of Z3 given Z1 and Z2 times probability of Zn given Z1 all the way to Zn minus 1. Is this last equation suspicious to you guys, or is it fine? This is just I'm just splitting the n random variables into parts. Okay, this is a factorization. It doesn't have to be this way. You can start with any random variable, let's say Z5, and then Z4 given Z. You can start from one random variable and condition everything else on the others. Okay, I could do the opposite, right? I'm just saying that you could start with Zn times probability of Zn minus 1 given Zn. That's a different factorization. Okay, this is just a factorization. So this is not saying anything more than what the joint distribution expression was saying. Okay, this guy, but from here to here. Okay, so let me just write, this is 1, this is 2, and this is 3. So from 1 to 2 there is no change. I mean, it's just any factorization is true, so 1 and 2 are equal. From 2 to 3 there is some assumption. Okay, the assumption is that probability of Z3 given Z1 Z2 is actually equal to probability of Z3 given Z2, right? So this term here, right, this term should correspond to some term there which involves probability of Z3 as well, but there it says probability of Z3 given Z2 only, because substitute I is equal to 3 and C3 given Z2, right? So I'm assuming something when I go from 2 to 3 is what I'm suggesting. Okay, I'm assuming that given Z2, Z3 is independent of Z1. Okay, so conditioning on Z1 has no influence on what Z3 takes. Okay, this is just a refresher for some of you who have already seen like this probability refresher, at least on the syllabus page, or people who already know this. I'm just saying, and in fact, if you look at the last one, Zn in general could depend on all the Z1 to Zn minus 1, but I'm saying that it only depends on Zn minus 1. Okay, doesn't depend on all the things before. Okay, the thing in this box, the number 3, is what's called I mean, it has what is called the Markov assumption. Okay, Markov assumption. It just means that the immediate preceding random variable is the only one. So given the value of the immediate preceding random variable, the current random variable doesn't depend on anything in the past. Okay, so Zi given Zi minus 1 doesn't depend on Zi minus 2, Zi minus 3, and so on. Okay, so that's a 3 is special additional assumptions needed from going from 2 to 3, whereas 1 and 2 are just the same. Okay, any questions about this? Okay, so actually once you get right 3, then it doesn't have to be 3, but once you write 1 or let's say 3 with additional assumptions that we made, you can just do maximum likelihood estimation at this point. So lecture 6, so you have a sum joint distribution of a bunch of random variables. In fact, in our data, the random variables took some specific values, right? Z1 took some value little z1, Zn took some value little Zn, and so on, right? Then you can just maximize the likelihood of that joint distribution if you can write this p theta of if you can write 1. Okay, so for example, what would be a joint distribution? Let's say you have 10 random variables. What is an example of a joint distribution, a simple joint distribution that you know of 10 random variables? Multidimensional Gaussian, like a Gaussian with 10 coordinates, right? With some zero mean and some covariance matrix sigma, covariance matrix, okay, is an example of a joint distribution over 10 random variables, right? Then you can estimate the parameters of this joint distribution, which would be the means and the covariance matrix. Okay, so that theta could be the means, 10 means and 10 cross 10 dimensional covariance. Okay, is that clear? I mean, we're not going to really do this, but this is just a unifying view of, you've already done MLE, you already know how to write a likelihood of a relationship between a bunch of random variables, and in time series we are explicitly capturing certain certain subsets or some subclasses of these relationships. Okay, so time series is nothing but some additional assumptions like 3 that you make on the joint distribution to make your life easier, and we'll see many other assumptions without even having this view. But at the base of it is just this joint distribution, and and if you have a parametric form, we just want to maximize the likelihood. Okay, and if you do that, you get the parameters. Okay, and once you get the parameters, you may care about what would be Zn plus 1 and so on. So that's kind of ill-defined at this point because the joint distribution is only defined with respect to Z1 to Zn. But once we get the parameters, we can do something. Okay, like we may have only observed Z1 to Zn minus 1. Then given the parameters, I can maybe guess what Zn could be and so on. Okay. Any questions on this slide? Okay. So what's this? The previous slide. So you write p theta from Z1 to Zn, and then you do MLE or whatever EM, and you get some parameters estimated. And if you know the parameters, you can find all sorts of conditional probabilities, like what is the probability of Zn given Zn minus 1, given, and so on, right? But many times defining this joint distribution is hard, this parametric distribution. I mean, I only gave one example, which is a multinomial, which is a multidimensional Gaussian. But in general, like more complex distributions, you can define them, but they are probably like hard to define a priori. Like if I observe a bunch of sales data, like what would be the joint distribution I can define? It's not, even if it's one dimensional. Okay, I've observed 10 sales numbers. What would be the, maybe they are increasing over time. Like which joint distribution would give me that data is kind of, it's not difficult, but it's something, it's an overkill, right? You only observe 10 numbers and you're thinking of like 10-dimensional distribution maybe. So there are some simpler ways, relatively simpler ways to also describe relationships. And I've already mentioned that previously, the previous example I gave at the first slide was correlations. Okay, and for the next 5 to 10 minutes, we're going to talk about how to use correlations to define relationships between random variables. Okay, and then use it for time series problems like forecasting and smoothing and whatever the types of tasks are. Okay, so I guess simpler depends on, it's a relative thing, but focus on moments are basically things like expectation of zi's or correlations between zi, zj, and so on. Moments are nothing but these expectations of a bunch of random variables. Okay, so first moment is the expectation. Second moment is just a variance. There are raw moments and central moments and stuff like that, but they just is a name for saying there's a bunch of expectations. Okay, so the simpler approach is to focus on moments, and in fact we'll just look at first and second moments, so just means and covariances. Okay, or correlations. And before so we'll focus on moments. In fact, we'll look at another key property. In fact, we'll look at certain types of random variables. Okay, so moments. So if I tell you the expectations and covariances, they restrict me to what types of random variables I'm considering. For example, if the expectations are all 0 and the correlations are all like pretty small, then I know that these random variables are probably limited in the sense, of course, if I know the expectation is 0, then it has to be 0-centered distribution. No, so that's not true. But Okay, so moments, what they do is they impose certain restrictions on the distributions that you consider. Okay, if the mean is 0, then of course the distribution should be such that it's, if you write the integration of x p of x dx, it has to be equal to 0. So there is no, there are not too many p of x's which will which all fit this equation. Okay, there are only some p of x's which will fit this equation. That's all I mean by saying that the moments restrict the types of distributions you're considering. Okay, I guess that's hopefully clearer. Okay, what we'll do is further restrict our consideration to only certain types of moments, a certain type of expectations and covariances, which kind of together define what are called weakly stationary sequence of random variables. Okay, so what are we doing now? We said joint distribution is too hard, let's think of moments. Even within moments, let's think of even some restrictions on moments. Okay, and these restrictions, as a basket, I'm going to call them weakly stationary assumption on a sequence of random variables. A sequence of random variables is nothing but that z1 to zn. Okay, it's also people like to use the word stochastic process. Okay, stochastic process just means it's random process. Random process just means a sequence of random variables. Okay, so the sequence of random variables is not a mystery. So what is weakly stationary? Okay, so weakly stationary, a sequence of random variables is called weakly stationary if its expectation. So I'm going to index the random variable zt. T is a time index. I mean, is an index. Previously I was using i's, so let me just use t's just to kind of allude to that we are thinking of time series. So expectation of zt is a constant. I mean, is equal to mu. Okay, think of like a Gaussian distribution with mu, and covariance between zt plus tau and zt is equal to some gamma tau less than infinity. Okay, I mean this is also is constant, and this depends on tau. So I'm further restricting. So there are many distributions which may all have the many joint distributions such that each random variable in that joint distribution may have the same mean. Okay, and further, among those distributions, we want those distributions for which the covariance between two random variables, maybe the first guy and the third guy, first guy and the 10th guy, those covariances only depend on the index difference between those random variables, which means that if I'm considering z1 and z3, then the covariance only depends on I'm considering 1 and 3 rather than other guys. Okay, any questions about this? So this is just a further restriction of, okay, I'm only going to think of certain distributions, joint distributions, which have this additional properties, and this is called a weak stationary property. Okay. So why is this called weak stationarity, or weakly stationary random sequence? Is because this allows us to model. This allows us to. So let's say I have a bunch of random variables z1 to z10. Then I can actually think of the joint distribution between z1 to z3, okay, and the joint distribution between z4 to z1 to z3, z4 to z7, and the joint distributions are the same. Okay. That what I said is called strongly stationary, and we're not saying that the joint distributions are the same. We are saying that there is the covariance and the first moment, so the mean and the covariance, they are functions which don't exactly depend on which location you are in. So the time index for the covariance doesn't matter. Okay, so the covariance between z10 to z13 is the same as the covariance between Z4 to Z7. Okay, so it doesn't matter which part of my, like let's say I have a sequence of like, you know, in this case 13 random variables, then it doesn't matter which part I'm zooming in and asking for covariance information, it's the same number. Okay, if I ask for 4 versus 7 and 10 versus 13, it's the same number. Okay, so that's why it's called weakly stationary, and it's going to be useful for yeah, I mean, because we know that, you know, if I zoom into one part of the time series or bunch of random variables, and let's say I estimate the covariance, okay, somehow, and I estimate the mean as well, then because of these two properties, I know that any other part of the time series, I know that the mean is going to be the mean that I estimated, and the covariance between two random variables that I'm not seeing, let's say in the future, okay, is going to be the same as what I've already estimated. Okay, so there is some transferability that I can do. Okay. Any questions about this part? So this will be helpful in, I mean, we're going to tease out more about this weakly stationary sequence of random variables, you know, a little bit more. But any questions about what we did so far in the funnel joint distribution to moment-based restrictions, and further, you know, even more restrictions? So it gives us something called weakly stationary joint, you know, sequence of random variables. Okay. Yeah, and in the time series, I guess terminology, this covariance function between random variables of the same type, for example, sales numbers, you know, across months or weeks, this covariance is a function of, now, you know, in this case, just a function of the lag. Okay, just function of tau, which is just a, you know, like a difference between two time indices. This is called the auto covariance function. Okay. Why is it a function? It's a function of tau. Okay, lag. So auto covariance with a lag of 1, lag of 2, lag of 3, lag of 10, you can evaluate it. So I'll evaluate to something, and auto because it's the same type of random variables, z's, right? Okay. I mean, just I guess to differentiate between cross covariance or cross correlation, things like that. And the variance of WT, sorry, not WT, ZT is equal to gamma 0. Okay, just by the definition, right? So if you just substitute tau is equal to 0 in the previous slide, right, tau is equal to 0, then I'm asking for the covariance of ZT with itself. That's just the definition of variance. So the variance is nothing but gamma 0. Okay, so they're saying that these bunch of random variables, they all have the same mean and they all have the same covariance. They all have the same variance, and covariance only depends on the difference between how, you know, how far away I'm relating them with. Okay, so that's variance, and so there's this auto correlation function, which is written as rho tau, which is gamma tau divided by gamma 0. Okay, this is so why is this true? Is this because the correlation between, let's say, z1 and z4, two random variables, is going to be, okay, expectation of z1 minus so z1 minus mu, z4 minus mu, divided by the variance of z1 variance of z4 square root, right? This is just a definition of correlation, huh? It's a definition of correlation. So we know what the variance was, you know, gamma naught, and we know what the numerator is. It's gamma tau. Okay, so that's it. That's what, you know, that's a simple definition for correlation and covariance. Now, So what are some examples? So example one of a weakly stationary sequence of random variables is simply IID zero mean with some constant covariance random variable. So think of IID normal distribution, standard normal. Okay, so if it's standard normal, then we know that its expectation of the t is 0, standard normal, right? And in fact, the variance of zt is 1, right? It's the standard normal, and write this. So gamma tau is 0 for tau is equal to 1, 2, all the way to whatever infinity, right? It doesn't. I mean, if things are independent, then the correlation for sure is 0. Okay. So this is an example of a weak stationary random. In fact, it's strongly stationary, and this is also called. I mean, this not this, but in general, let's say this is sigma square, and okay, here it did not say IID with mean this and variance something. Okay, so these are called white noise sequence. Okay, so if you draw the function of gamma tau, it will be 1 at 1 or sigma square somewhere, and then zeros at all the tau. Tau is on this axis and gamma tau is on this axis. Autocorrelation, autocovariance, and this is how the function would look like. 1 at some point, 1 as a sigma square at some point, and zeros everywhere else. Is the example clear? Okay. Here is another example which doesn't yeah, here is another example. Let zt be white noise. This sequence of sequence of random variables. Let this be white noise, and let S0 be equal to 0 and St be Z1 plus Zt. Okay, so it's a sum of, so it's like an increasing sum of so Zt is already defined. It's a white noise sequence. I'm saying as this, I'm now defining another sequence of random variables, okay, where S0 is just 0, but S1 is equal to Z1 itself. S2 on the other hand is the sum of the previous 2, and S3 is the sum of the previous 3, and so on. Okay, so this sequence, so this is also another sequence. This leads to some sequence of random variables, right? This is called a random walk. Okay, this is called a random walk sequence, and the covariance between St and St plus tau okay, I need to check this, but t times sigma square. Okay, I don't know if it's t or okay, some covariance. So this doesn't, okay, this random walk, okay, it's t times sigma square, and that's why this example would be an example, not this one, but this guy would be an example which doesn't conform to the weak stationary definition that I mentioned. Okay, the weak stationary definition that I mentioned requires that the covariance between two random variables just depends on the index tau, the difference tau, but here it depends on t. Okay, so it's not a weak stationary random variable in the sense that so what's the high level takeaway from this weak stationarity and this guy not satisfying weak stationarity is that for this sequence of random variables, it's difficult to kind of make any sort of predictability, because as I said, remember, if I had weak stationarity, then if I make some estimations on some part of the sequence, like covariance and means, then I know what the means and the covariances are in some other part. So think of that other part being the future, and this part where I could estimate is the past. Okay, so given data, I estimated something. I can use those estimates to say something about the future. Okay, for weakly stationary random variables. Whereas here I cannot do that because it's essentially random. So if I'm at S, if I know all the Z1 to Z10, and therefore I know S10, which is the sum of all these guys, I don't know what S11 is going to be because the Z11 is random, it's independent. Okay, it could be any value, it could be positive 100, it could be negative 50 or whatever. So there's no predictability. Okay, so that's a deal breaker for time series analysis. There has to be some, like if you think of returns on a for a stock, they better not be a random walk, because then you cannot really say anything about returns for tomorrow, given all the returns that you've seen in the past 1 year, for example. Okay, and so stationarity or weak stationarity, it's fine. So stationarity in general, it allows us to average across time. We can average across time and estimate parameters of my joint distribution. Okay, so so this is, by the way, an important idea, and there's a different version of it which is easier to parse in terms of joint distribution, but let me explain it this way. So let's say we observe sales data. Okay, we observe 10 numbers, right? That's 10 numbers, each number for a realization of a random variable. Okay, so each random variable just realized once. Okay, Z1 realized once, Z2 realized once, Z10 realized once. Okay, but I can use these 10 numbers to estimate the mean of Z1, although the other numbers are not related to Z1. Z1 was only like one little Z1 which realized for Z1. Okay, so I can do a time averaging to estimate some properties of any part of any even single random variable or pairs of random variables and so on, anywhere. Okay, so that's not something that you've seen before. Okay, where you're using other observations of other random variables to estimate parameters of some other, like maybe just the first random variable or just the first and second random variable. And that's not too surprising because we just assume that expectation of z's is the same number, so I can actually I can use the other random variables data to actually estimate the mean. Okay, so that's the key idea here. Any questions? So okay, so how this is average, and therefore estimate gamma tau. Let's say gamma 1, gamma 0, and gamma 2. Let's say I'm only interested in these three numbers. I can estimate that irrespective of what part of the sequence of these random variables I have realizations for. And in fact, it's just one realization. Let's say I can just use one realization of different random variables to estimate these overall quantities. Okay, these special quantities that I had for weak stationary distributions. Okay, so I can estimate gamma tau or whatever mu. How do you actually estimate them? It's the usual thing that you've seen. So gamma, tau, and mu. For example, mu could be just the average of little zi's. I is equal to 1 to n, for example. And gamma tau, similarly, you know how to estimate covariances, right? Just put the hats or empirical quantities instead of true quantity instead of the true values. These are like plug-in estimators, I guess that's what they're called. So you can estimate them. So let's not write those formulas. So next we are going to describe. So that was just a saying that if you had these weak stationary random variables, all you care about is estimating the mean and estimating this gamma tau, and you're done. And you can estimate them from different parts of your time series. Okay, so that's a very simple. That's like not even, I haven't even specified any specific distribution or anything like that. You just wanted to get gamma tau and mu. You can get that from given a sequence of observations. If the observations actually are coming from a joint distribution which satisfies the weak stationary conditions. Okay, that's one example. Now we're gonna study two, I guess, classical time series models. The first one is autoregressive model, and the second one is moving average, and then we're going to merge them together to get what is called the autoregressive moving average model. Okay, so these are examples of linear time series models. Okay, I'll tell you what linear just means. In fact, okay, linear just means that the random variable at time t depends linearly on the random variable at time t minus 1, t minus 2, and so on. Okay, so there is a linear relationship between random variables. It's like saying y is equal to beta transpose x. I said, there's a linear relationship between x and y. So y is like a linear combination of a bunch of x values, right? So similarly here, linear just means that random variables are related to each other, but they are related to each other in a linear way. Okay, and let me in fact elaborate on AR, autoregressive model. So AR and MA actually have parameters. Okay, so I think the parameters I use are let's say P and Q. Okay, so we're going to look at AR1. So P and Q, just think of them as positive integers, so going from 1 to all the way to infinity. Okay, so AR1, AR2, AR10. Okay, for all intents and purposes. So what is AR1? So AR1 assumes that the random variable at time t, I'm switching notation, so I'm using W's now. Random variable at time t depends linearly with some multiplier. So think of this number as a 0.4 for simplicity, times Wt minus 1 plus epsilon t. Okay, so random variable Wt depends on two other random variables in a linear way. The coefficient for one of the guys is phi. Let's think of it as 0.4. The coefficient for the second guy is 1. Okay, and in fact, what is this epsilon t? It's coming from this bunch of epsilon t guys, which are white noise. Okay, by which we just saw, I think in the previous slide or 2 slides ago, that the expectation of epsilon t is 0, and the variance of epsilon t is, let's say, sigma square. Okay, so this is an example. This is essentially what an autoregressive model is. So it is again relating multiple random variables. We saw joint distribution. We're relating via moments. That's one way to see. And here we are saying, in fact, they're related exactly in a linear way. Okay. If you know Wt minus 1, still you don't know exactly Wt because there is epsilon t there. Okay. So they are related, but they're not deterministic. So if you know Wt minus 1, it's not like you know Wt and so on. Okay. Further, if we assume that epsilon t is independent of Wt minus 1, Wt minus 2, and everything else, maybe W0 all the way to W0. So this is a notation, I guess, short form for independent. Okay. Then the probability of W1 to Wt is equal to the product of t is equal to 2 to I guess this is t. Let me make it n. T is equal to n, probability of Wt given Wt minus 1 times probability of W1. So we saw this before. Okay, just one consequence of just a consequence of this observation actually. Okay, you don't need this type of linearity and all that to say something has this particular product form, but under that linear normative model, and because epsilon t is independent of wt minus 1, wt minus 2, if we only look at the joint distribution between w's, the wt given wt minus 1 doesn't depend on anything else, doesn't depend on wt minus 2. That you can see directly from the expression, right? That linear expression doesn't there is no wt minus 2. Okay. Given wt minus 1. Of course, I can write wt minus 1 as again phi times wt minus 2 and all that, but we are not doing that because we want to give, I mean, as in fix the value of wt minus 1. So it's not like I can I don't want to introduce wt minus 2 into the equation. But this is an example of, this is what I said was a, I mean, I guess in this case the sequence is called Markovian, the capital M actually, and my handwriting is bad, so let's see. Okay. So in this autoregressive one, AR1 model, I mean, this is a model of, I mean, it's called a model, it's just a relationship, description of the relationship between random variables. In the AR1 model, if you back substitute, I mean, instead of wt minus 1, substitute phi times wt minus 2 plus epsilon t minus 1 and all that, then you'll get wt, epsilon t anyway you can't back substitute in any case, you will get the following expression. So let me back substitute once, plus phi times phi of w t minus 2 plus epsilon t minus, is this correct? T minus 1, yeah, t minus 1. Okay, so this is one level back substitution. This will give you epsilon t plus phi times epsilon t minus 1 plus phi square w t minus 2. So this you can just do several times. So you'll get epsilon t plus phi times epsilon t minus 1 plus phi square epsilon t minus 2 all the way to phi to the power t times w0. Okay. So you can see that you know, so this is wt. You can see that if I'm looking at this linear model, if I have w100, it's a sum of 100 random variables. Okay. If I'm looking at w1000, it's a sum of 1000 random variables. Okay. So it's like, it looks like I'm increasingly adding too many numbers on top of each other. Okay. So if I have lots of numbers, I'm adding them together, then the summation may explode, as in it may take large and large values. So we need a condition, which is that the phi value should be less than 1. Okay. For at least phi value should be less than 1 for these guys to be small. Okay. So wt to be finite. Okay. At least, you know, in addition to phi values, epsilon values could be random variables which are like bounded. For example, Bernoulli random variables, they are not taking values, you know, which are too high or too low, like 0 and 1 or minus 1 and 1. In addition to that, you also want phis to be small. Okay. In fact, small in the specific sense, they have to be exactly less than 1 for large sums to be not exploding. Okay. That you have seen, like a bunch of numbers, they should not have, they should, for example, if you have a bunch of numbers but they're all greater than 1, then you are in a bad situation. Okay. So here we're just saying that epsilons can be, you know, some value within a range, you know, some minus a to a, but as long as phis are small, strictly less than 1, then the whole summation, we know that it's not gonna blow up, like w1000 or w million will not blow up. Okay.
So if it's greater than 1,
yeah,
say for t minus x time, would you ignore it from the equation, or?
No, we don't want, so we don't like that those models where it's greater than 1. So we are saying that we would prefer for AR1 that phis are less than 1.
But that you can't predetermine that condition and only get the equation that gives you that condition, but you have to evaluate the entire thing.
Yeah, I mean, so if you are trying to learn a phi for a model, so we'll see how, maybe we'll see how to learn phi. then if the phi is like dangerously close to 1, then maybe R1 model is not the right model. Yeah. So what is the expectation of WT? What's the expectation of WT? What do you guys think? It's a bunch of random variables. So expectation of a bunch of random variables is expectation of the sum of a bunch of random variables is the sum of the expectation of these random variables, right? So you can take the expectation with respect to epsilon t. Epsilon t we said is white noise, so its expectation is 0. Similarly, epsilon t minus 1, expectation is 0. So you go all the way to just W naught, and I think we assume W naught as 0 mean. If we have not assumed it, then it's just expectation of W naught. If we have assumed W naught to be 0 mean, then the expectation of WT is also 0. Okay. Actually, W naught, just think of it as equal to some epsilon 0 as a limiting case, right? You have to say, I mean, in the equation it's relating 1 to some previous indices. So and similarly, so what I'm trying to demonstrate now is that this autoregressive 1 process is also weakly stationary. Okay, so we are looking at expectations; they are all taking the same value. So WT has the same expectation 0, WT minus 1 has the same expectation 0, and also the auto. I don't want to write autocorrelation function, so let me just use gamma tau is the correlation between covariance between WT and WT minus tau, right? So this guy in the notes it's worked out, but it's just sigma square times phi to the power tau divided by 1 minus phi square. Okay, some number which depends on the phi, the parameter of that linear model, and sigma square, which is the variance of that white noise sequence epsilon t, and it only depends on tau. Okay, I mean it only depends on it depends on, of course, the parameters. I mean some fixed numbers, sigma square, phi, and sigma square and phi. Beyond that, it doesn't depend on the index themselves. It doesn't depend on t or t plus tau. Okay, so this is an example of a weakly stationary sequence of random variables. Okay, but here we know more because we explicitly know how the random variables are related to each other through that linear equation here, this linear equation. Okay, so we are increasingly becoming more and more specialized. Okay, we said weakly stationary already imposes so many conditions. I mean, means being the same, covariance doesn't even depend on time indices. On top of that, we are saying that random variables are linearly related to each other. Okay, that's like the linear model of supervised learning. So many restrictions. Okay, and the second example. So we're going to switch gears and talk about a slightly different linear model, moving average, and then combine those two to get our first. I guess simple time series model. Okay, so let's look at moving average. So in the moving average version, as I said, there's going to be I mean, even for autoregressive, there was a parameter p. Okay, so maybe I didn't write that explicitly. So if you have p parameters, so here it was p, right? So p would just correspond to WT depends on phi 1 times WT minus 1 plus phi 2 times WT minus 2. You just add the previous p terms into the picture. Okay, the bracket 1 just means that it depends on one guy from the past. Okay, WT minus 1. Bracket 4 just represents WT minus 2, WT minus 3, WT minus 4 in addition to WT minus 1. Okay, that's 4 guys. So let's directly write moving average Q. Okay, MAQ. MAQ model would be that now these are different W's. Okay, these are not the same W. So but WT, we're going to write it as theta naught times epsilon t plus theta. Okay, so thetas are now some parameters, some fixed numbers, but I'm going to relate the random variables now. So WT is related to some q random variables, which are these guys, theta naught times epsilon t, theta 1 times epsilon t minus 1, plus theta q times epsilon t minus q. Okay, so these are actually q plus 1 random variables. Okay, so they're q plus 1 random variables, and it's the same. So these epsilon t's are still the white noise. Okay, and so this is an example of a moving average model. So the difference is that here Wt doesn't depend exactly on Wt minus 1. Okay, it depends on, there are some, so Wt minus 1, let's say, let me write it actually. So if you write Wt minus 1, that's going to be equal to theta 0 times epsilon t minus 1 plus theta 1 times epsilon t minus 2 plus few guys plus theta q times epsilon t minus q minus 1. Okay, yeah, so there are a bunch of common random variables like this guy, and this guy and this guy somewhere. Okay, right, they're common random variables, but Wt is not exactly, is not a constant, is not a multiply, it's not a number times Wt minus 1, because this guy has some additional random variable, and this guy has some additional random variable. So there are two random variables which are different between those two. Okay, there's some common t minus 1 random variables, but both guys have some different random variables, and they're not right like next to each other. One is somewhere else and one is somewhere else. Okay, so even here the expectation of Wt, it's clearer here that it's 0, right? It's just each one of the epsilons is white noise, so it's 0, and gamma tau, which is the covariance, autocovariance function, is I guess more involved. So it's sigma square times sum over t is equal to 0 to q minus tau of theta t times theta t plus tau. Okay, for tau between 0 and q. Okay, it's some expression, but here you can see that, okay, I should not have used t maybe, so let's use k. K is just a running variable. Okay, it's taking some few number of values. So you can see that gamma tau only depends on tau, doesn't depend on the actual time index of the original random variable, like the autocovariance between, or the covariance between random variable Wt and Wt minus 10 doesn't depend on t. Okay, it's the same as Wt minus 1 and Wt minus 11, okay, the shifted ones. So these are two examples of weakly stationary sequences, and in addition to that, they also, I mean, they make, because of the linear structure, they are satisfying the properties, linear structure and white noise, okay, in the mix, and in the specific linear structure is letting them be the weakly stationary random variables, weakly stationary sequences. Okay, now these are assumptions about how, these two models are actually assumptions about how random variables are related to each other. For example, in autoregressive 1, we are saying that maybe the previous day's sales times some constant like 0.9 times the previous sales plus some noise is going to be my prediction for what the next day's sales could be. Okay, so if I know that 0.9, I could know, okay, previous sales was 100 units, then the next day's sales is 90 times, so 0.9 times that 100, let's say 90, plus some white noise with some variance. Okay, so that's an example of a I mean, that's how you would use it in your application. Note that when you get the sales data, they may already have some sort of a linear, some sort of a trend. Okay, so this is a word in time series analysis. There may also be a trend in the data, which just means that the trends. So there are two words: trends and seasonalities. Okay, are predictable. Yeah. Patterns in the sequence, or not in sequence, in the data. Okay, so trends. So we saw that NASCAR data, right? So where is this? So here, those lines, the black lines are fits to, are essentially like trend lines. They are looking at parts where it's like very predictable. Okay, so if I know, if I'm at lap whatever this is 120, then I know at lap 200 there's a trend, linear trend going upward. So I can tell you what the lap time in the 200 laps could be. Okay, so that's a trend. There is seasonality as well. So in the sense of some sort of a up-down, cyclical pattern. So here, like that zigzag pattern in this case, or in general for other data, there will be some sort of a cyclical pattern, a repeating pattern. So those are predictable. I'm just calling them predictable patterns in the data. What if you have this times? You have some data, sales data. First, you find the trends and seasonalities using some other methods. Okay, trends. How would you find? You can. Okay, so there are certain ways to isolate trends in the data, and certain ways to find seasonality. Seasonalities you can find by, for example, doing a Fourier transform of your data. Like if you have one sequence of one-dimensional data, then you can take a Fourier transform to see what sinusoidal patterns exist in this data. Okay, maybe there's a seasonality between like sales are higher in the summer, lower in the winter, higher in the summer again, and so on. Then you can find that sinusoidal pattern by just taking Fourier transform, for example. But that's not the only way. There are 100 different ways to find seasonalities and trends. First, you find seasonality and trends. Those would be some functions. So if your data is original data is ZT, okay, from which you find trends. Okay, so trend will be a function of time, and seasonality will also be a function of time. Seasonality is a function of time. Then you subtract those two. So ZT sequence minus trend plus seasonality. Okay, these two guys. Then whatever remains, that's the part which is unpredictable. Okay, and that's the part where we can assume things like what we assumed in the previous. That's the part where we can assume the weak stationarity models that we saw before. For example, autoregressive or moving average, and so on. Okay. So I mean, that part you can try to model it using weak stationarity sequence models that we saw. Okay. Any questions?
You said this is unpredictable.
Unpredictable in the sense, in a certain way, you can predict it. I mean, in a sense, autoregressive, like we just saw that, for example, autoregressive model. Where is it? Yeah, we said given WT minus 1, I have an idea of what WT is. I mean, I know the distribution of what WT is. Okay, given WT minus 1, it doesn't depend on everything else. If I know that this conditional probability, then I can find its mean. Okay, but you know that given WT minus 1, WT's mean is actually 0. Okay, I mean, which is fine, but that's like it's like saying, sorry, not 0. Given WT minus 1, WT's mean is, phi times WT minus 1. Like, let's say, I mean, in the previous example, I was telling WT minus 1 is 100, then phi times 100, phi, let's say 0.9, that 90 is the mean, okay, of my expected value of WT. Okay, that's predictable, sure. but you will not be able to pinpoint beyond that. So pinpointing beyond the means and the covariance or autocorrelation that autocovariance I'm talking about is not possible in this model, because we are not really assuming anything more, right? There's either that's white noise and there is a linear structure. So that's what I mean by like not unpredictable, where its trend is like a literally deterministic function, right? Some function of time. So at time t there's 100 sales, at time t plus 1 there's 120 sales, at time t plus 2 there's 140 sales, and things are going up. Okay, so and so before I start reviewing some things, so the last part is we'll combine autoregressive and moving average models, the two linear models, to get the ARMA model. Okay, and what is the linear equation here? It's going to be that Wt, so I guess ARMA p comma q in general. So Wt is going to be I don't want to write a summation, let me just write. So phi1 times Wt minus 1 plus phi2 times Wt minus 2. Let me actually do p is equal to 2 and q is equal to 2. Okay, plus theta 1 times epsilon t minus 1 oh sorry, I missed one term, plus epsilon t plus theta 1 times epsilon t minus 1 plus theta 2 times epsilon t minus 2. Okay, so this is the representation for a ARMA 2,2 model, and the model's parameters are of course thetas. We already, and of course the we assumed epsilon t is white noise, so it only has one parameter, which is sigma square, which is the variance of that guy. Okay, so sigma square and these four numbers completely characterize this model, right? So why do we why did we even combine this, and what's the significance of the moving average model or the autoregressive model? The key idea is that AR models capture certain types of covariance functions. So AR models capture certain gamma tau patterns. Okay, so for example AR1 we saw it was like 1 here or whatever, sigma square here and then zeros here. Okay, right. Similarly, moving average gamma tau, it will also have a for example, it could depending on the phi values, it will have maybe something like this, some pattern. Okay, some few numbers. We saw this, right? Between tau is like greater than or equal to 0 and up to q, there will be some numbers, and everywhere else it's 0. Okay, zeros. This is AR1, I guess. I mean, it doesn't have to be like this. It could be some numbers like this. But in fact, it will go all the way to yeah. I mean, depends. Okay. Anyway, some distribution. So they capture different covariances, and by combining autoregressive and moving average, we can capture much more richer covariant autocorrelation functions. Okay, that's the idea. So things like we're increasing for some time and then decreasing, and so on. Okay, so that's the idea behind combining them. Yeah. Okay, so yeah. Okay, this is fine. So I will not spend more time on ARMA models because there's a lot more detail, and I think we are running out of time for this time series section. But what I've not discussed is tying it back to supervised learning, that I'll immediately do right after. But one last thing is how to estimate this phi1, phi2, theta 1 and theta 2 and sigma square. So these are the parameters of this model. Okay, so there are special methods which we will not go into. I'll just write the name of the method. One example name of the method. It's called Yule-Walker equations. Okay, to estimate these parameters. And I don't want to say more on this, but actually I want to spend more time on relating this to supervised learning. So there are some ways to estimate this method. So actually this Yule-Walker equations, you can get it if you just these are a bunch of system of equations where the things that you need to figure out are these parameters like phi1, phi2, theta 1, theta 2. Okay, how did you get these equations? You can always start from scratch, write a maximum likelihood estimation problem, and the MLE problems, take the first derivative and set it equal to 0, and you'll get these equations. Okay, that's one way to get to Yule-Walker equations. But so that brings me back to the original point that time series methods are just a very a way to handle the complexity of describing the joint distribution between random variables. So if you are more comfortable with directly working with joint distribution between random variables, the subsequent discussion about stationarity and so on is of course very important, depends on types of data that you have. You could just unify, view at these things directly in terms of joint distribution, maximum likelihood estimation, and that's it. Okay, so which you already seen, on lecture 6 and lecture 7 and so on. And another thing is that our base object here, we said z1, z2, z3, there is an order relationship between them, and there's a temporal relationship basically between them. Whereas when I was initially contrasting with supervised learning, I said these observation units, they are not related to each other. We kind of assume things are independent, okay, independent from p of x comma y. But you can view these sequences, let's say short sequences, so z1 to z5 as your first observation, okay, z2 to z6 as your second observation in supervised learning land. So z3 to z7 as an observation in the supervised learning land. Then you can look at, okay, does z1 to z5 have some patterns? Okay, that's your features. So does z1 to z6 have some patterns? It's going to be your features. The z5, z6, z7 could be your prediction. So you can transform. Okay, let me actually explicitly say this: z1, 3, z4, let's say z100. I can transform this thing into a supervised learning problem where I can take some strings, like for example, I can take z6 and say that I'm going to predict it using some function of z1 to z5, okay, and z7 as some function of z2 to z6 and so on. Okay, then if I consider now these bunches of random variables, then I can capture some patterns in them, some temporal patterns. Okay, like for example, think of seasonality is essentially like, for example, it could be the day of the week or the time of the day or month. Okay, that's you can just add indicator features in your feature vectors, saying whether it's indicator of which month it is, or indicator of whether it's a weekday, indicator of whether it's a weekend. Okay, so you don't really have to think of like a time series model of sales where you actually capture seasonality without knowing, using the like ARMA model and so on. You don't have to do that. I mean, you don't have to explicitly extract out seasonality that way. You can actually just think of, you have time series data, bunch data together, and that's your mega feature vector or bigger feature vector from which you can create features like indicator of time of the day and so on. Okay, so I mean that's in general I wrote it this way. Okay, this function is your prediction function, for example, and some transformation of these like a sequence of observations would be your one observation in the supervised learning setting, whereas this would not be one observation in your time series model. This would be like 5 observations in your ARMA model. Okay, so that's one way to relate supervised learning back to time series methods. Okay, so any questions about the very extremely brief introduction to time series? So it's a particular point of view where we're saying joint distributions are tough. Let's look at moment conditions, and then there are simple models like ARMA, and there are much more complex models as well. And each model comes with its own way to estimate the parameters. Like in ARMA's case, there is the Yule-Walker equations is one popular way to estimate, but you can also do it using maximum likelihood and method of moments, and there are various methods to do so. And that's kind of the very brief overview of time series methods. Okay, we barely scratch the surface, but that's the idea. Any questions about this statement about time series? Was it too fast, too slow? Okay, so what we'll do next, let's take a break for 7 minutes, and then we'll spend the next 50 or so minutes on the reviewing what's there for the exam.